All right, welcome. Today, we're going to pull back the curtain on the strange quantum rules that secretly run, well, everything. And we're basing this whole deep dive on the fascinating research of Dr. Sudhyendra S.G. Now, that might sound like a riddle, right? But the answer is way weirder than you might think. It all comes down to a bizarre set of rules that run the show at the teeniest, tiniest scales of the universe. So let's get into it.
Okay, so to really wrap our heads around the quantum world, you've got to do one thing first. Forget everything you know about smooth, gradual ramps. Instead, I want you to start thinking about stairs. Seriously, this one little mental shift, it changes absolutely everything.
So, in our big world, the world we see every day, energy seems like a ramp, right? It's continuous, you can be anywhere on it. But the thing is, down in the microscopic world of atoms, it just doesn't work that way. Energy comes in these fixed, separate steps. It's literally a staircase.
And this right here, this is the absolute core rule. Think about an electron in an atom. It can only have very specific amounts of energy. It can be on step 1 or it can jump to step 2, but it can never, ever be found floating somewhere in between. That's not just a suggestion, it's a fundamental law of physics down at that scale.
You know, this whole idea has a name. It's called energy quantization. It's the principle that energy comes in these distinct packets, or quanta. It's kind of like how on a piano you can play a C or a C sharp, but you can't play the note that's in between them. And this isn't just some wild theory, okay? It's as real and as fundamental to our universe as gravity is.
Okay, so an energy staircase for electrons. Who cares, right? Why does this even matter? Well, it matters because this one single rule is the reason you see color. I mean all color. The vibrant, brilliant colors all around you every single day. Yep, it's this.
So let's picture this. An electron gets a little jolt of energy and it jumps up to a higher step on that staircase. But it can't stay there forever. It's not stable, so it's going to fall back down. And when it does, all that extra energy has to go somewhere. So what does it do? It spits it out as a tiny packet of light, a little particle we call a photon.
And here it is. This is the magic part. The size of that jump down determines the color of the light. It's that simple. If it's a big drop, a lot of energy gets released, and you get a high energy color like blue or violet. If it's just a small hop down, less energy is released, and boom, you get a lower energy color like red or orange.
And this isn't just some abstract idea. This is the tech in your life. You ever wonder why a neon sign glows that specific iconic red? It's because the energy steps in neon gas have that exact size. Or what about LED lights? The color of an LED comes from its band gap, which is really just a fancy way of saying scientists have built the material to have a very, very specific step size. It's quantum physics literally lighting up our world.
Okay, so if you thought that was a little weird, buckle up. We're moving on to our second quantum rule, and this is where things get, well, properly strange. If the first rule was about stairs you can't be between, this next one is about solid walls you can literally walk through.
Now, we all know how the world is supposed to work. It's common sense. If you roll a ball at a hill, but you don't push it hard enough to get to the top, what happens? It rolls up a little, and then it rolls right back down. It's never, ever gonna just magically pop up on the other side. Obvious, right? Well, what if that ball was an electron? If it was a quantum particle? Yeah, the story changes completely. Turns out, the quantum world couldn't care less about our common sense. See, the thing about quantum particles is that they're not just tiny little billiard balls. They also act like waves. And when that wave hits a barrier, a wall it doesn't have enough energy to climb over, something just bizarre happens. Sure, most of the wave bounces off, just like you'd expect, but a tiny piece of it actually leaks right through the barrier and just appears on the other side.
This completely impossible sounding feat has a name, quantum tunneling. And yeah, it's pretty much what it sounds like. It's the quantum version of you walking up to a solid brick wall and poof, just appearing on the other side. It is literally like a ghost walking through a wall.
But here's the kicker. This whole ghostly walking through walls thing, it's not just some weird party trick that particles do. It is an absolutely crucial, essential process that makes some of our most powerful technologies work. And it's even what makes life itself possible.
So get this. Quantum tunneling is how we can literally see individual atoms with things like scanning tunneling microscopes. It's how the flash memory in your phone or your computer stores data. It's the reason for radioactive decay, and, maybe most mind-blowing of all, it's the engine that powers our sun.
And the precision here is it's just staggering. Let me give you an example. With a scanning tunneling microscope, you have this incredibly sharp tip that you bring super close to a surface. Electrons then tunnel across that tiny gap. Now, if you move that tip just 0.1 nanometers closer, we're talking less than the width of one atom, the number of electrons tunneling across goes through the roof. By measuring that change, we can actually build a map of a surface, atom by individual atom. It's unbelievable.
But let's go back to the sun, because this is huge. Just think about this. The core of our sun is unbelievably hot, right? But here's the secret. It's actually not hot enough for protons to slam together and fuse on their own. They naturally repel each other too strongly. So how does the sun work? Quantum tunneling. It lets those protons kind of cheat. They sneak through that wall of repulsion and merge together. Let me be really clear about this. Without tunneling, the sun would not shine. No tunneling means no sunshine, and no sunshine means no us.
Phew. Okay, I know. That was a lot of pretty strange stuff. So let's kind of take a breath, put it all together, and go over a couple of the biggest questions that always come up when you talk about these weird, wonderful, and, fundamental rules of our universe.
All right, first up, and this is the one everybody asks, does tunneling break the law of conservation of energy? I mean, if a particle gets through a wall it shouldn't be able to, did it just get a free lunch, a free energy boost from nowhere?
And the answer is a big, clear no, not at all. Energy is still totally conserved. The particle doesn't gain a single thing. Its weird wave nature just means there's a non-zero chance, a probability that you'll find it on the other side of the barrier. But if you do, it has the exact same amount of energy it started with. No magic.
Okay, which brings us to the next logical question, right? If an electron can do this, why can't I? Why can't you just walk through a wall if you, just try enough times? Why don't we see footballs tunneling through the goal?
Well, it all comes down to probability. For a tiny little electron, the odds are, they're small, but they happen all the time. But for something big, like a football or you, the odds are so ridiculously astronomically tiny. I mean, you would have to stand there running into the wall for longer than the entire age of the universe, many times over, just for it to happen once. So while it's technically not zero, it's so close to zero it's impossible. These quantum rules are super powerful, but they really only run the show down at the atomic scale.
So let's just wrap this up. From the color glowing on the very screen you're looking at right now, to the light and heat coming from our sun, our entire world is built on this strange, spooky quantum foundation. These aren't just little scientific quirks, They are the fundamental engineering rules of our universe. And as we get better and better at not just understanding them, but controlling them, it leaves us with one massive question. What are we going to build next?